In this example, we have a very classic physics example. We have a person, maybe it's not classic in the sense that we're measuring a fish, but a person weighs a fish of mass 1.5 kilograms on a spring scale that's attached to the ceiling of an elevator. We want to know what is the apparent weight of the fish if the elevator is accelerating upward at 2 meters per second squared, if it's moving at a constant velocity, or if the elevator is accelerating downward at a rate of 3 meters per second squared. So in this particular example, we want to focus just on the fish, but we have to keep in mind that the scale itself is going to read whatever the tension is in the wire that's connected to the scale and then connected to the fish. So our goal then is to find the apparent weight, where the apparent weight will just be equal to whatever the tension is that's holding the fish up. This is similar to if the person was standing on a scale, like a regular bathroom scale, and you were asked to measure what the person's apparent weight is. In that particular case, it would be the normal force that we would want to find, because that would be the apparent weight. Okay, so what I'm going to do here is just draw a picture, sort of redraw the picture of the fish. So for the first part, for part A, if I draw a free body diagram for the fish, I have the actual true weight of the fish from the force of gravity, which is acting down, and that's just mass times gravity. So that would be 1.5 kilograms times 9.8 meters per second squared. And so the force of gravity is just 14.7 newtons. Now in this example, the elevator is accelerating upward. So this is a system where it is not in equilibrium, right? So the sum of the forces here are not going to be equal to zero, and in fact, whatever the direction of the acceleration is, that's also going to be the direction of the net force. So there has to be some net force that's also directed upward. So when I draw in my tension in my picture, I realize that my tension is going to have to be bigger than the force of gravity, because that tension has to be produce a force that's going to be bigger than that gravitational force to produce an upward net force on the fish. So if I consider this to be the y direction, I can look at the sum of the forces in the y direction on the fish, and that has to be the mass of the fish times the acceleration. So we know in this particular case that this upward acceleration is 2 meters per second squared. And so if I sum my forces, acting in the positive y direction, I have the tension. Acting in the negative y direction, I have the force of gravity. And that has to equal the mass of the fish times the acceleration of the fish. And since the fish is in the elevator, the fish is accelerating at the same rate upward, which is 2 meters per second squared. So the tension minus the force of gravity has to equal 3 newtons. So if I add 14.7 to both sides, I get that the tension is 17.7 newtons, and this is the apparent weight. We could actually use this same free body diagram for all 3 of these parts to the problem, but let's talk through it and see if we can draw the free body diagram with the lengths of the vectors appropriately. So in part B, the elevator is moving at a constant velocity. And if it's moving at a constant velocity, this means that the acceleration has to be equal to 0. And if the acceleration is equal to 0, it means that the net force acting on the fish also has to be 0. So this time when I draw my free body diagram with the force of gravity acting down, 14.7 newtons, I can draw the tension to be the same value as the force of gravity, the same length, because I know, if this is again my positive y direction, that the sum of the forces in the y direction are going to have to equal 0. So I have to make sure those two forces, which are the only ones acting on the fish, add up to 0. So the tension minus 14.7 is equal to 0, so the tension is 14.7 newtons. All right, for part C, we have the elevator is accelerating downward at a rate of 3 meters per second squared. So I'm going to go ahead and I'm going to draw my picture again. So here's my force of gravity, 14.7 newtons. And in my picture, I'm still going to choose my positive y direction to be up, just to be consistent. But what I realize is that the acceleration is actually pointing down. So if my positive y direction is upward, this means that my acceleration is going to have a negative value because it is a vector. And it also means that the net force is going to be in the same direction as the acceleration, which means it's going to be downward. So when I draw my tension in this picture, I need to make sure that I draw it smaller than the force of gravity because the net force has to be in the downward direction. So if I do the sum of the forces in the y direction equals the mass times the acceleration in the y direction, and I'm now going to go ahead and put in a negative sign there for my acceleration, the sum of the forces in the positive y direction is still the same. I have tension acting up, and then I have the force of gravity acting down, and this has to equal the mass of the fish times the acceleration, which is negative 3 meters per second squared. So the tension minus 14.7 has to be equal to negative 4.5 newtons. So the negative here just means that the net force is in the downward direction. So if I add 14.7 to both sides, I get that the tension is 10.7 newtons, 10.2 newtons, excuse me, 10.2 newtons. And this is going to be the apparent weight when the elevator is accelerating downward. So if the elevator is accelerating upward, then the scale is going to read more than the true weight. And if it's accelerating downward, it's going to read less than the true weight.